Good morning, friends. After the discussion of the exponential loop and the decay curve, now what is the activity of a radioactive sample and what is the equation? That means we are going to derive the different form of exponential law of radioactivity. Already we derived the equation n is equal to n0 e⁻² minus lambda t. And also I mentioned at the last, what is the activity at time t of a radioactive substance I is equal to I0 e⁻² minus lambda t. And this equation is also written in terms of the mass. M is equal to m0 e⁻² minus lambda t. Here, according to the NCERT book, the activity of a radioactive substance is denoted by capital R instead of the I. Therefore, R is equal to R0 e⁻² minus lambda t we are going to discuss. Therefore, the question is that define the disintegration rate or the radioactivity of a sample and obtain the relation capital R is equal to lambda n. Again, they define the disintegration rate of radioactivity of a sample and obtain the relation R is equal to lambda n. Now, the number of disintegrated nuclei per unit time in radioactive sample is known as the decay rate or the radioactivity. Again, the number of disintegration nuclei per unit time, that means the rate of disintegration, is known as the radioactivity R. Suppose at time t, the number of nucleus in a given sample is capital N, then the rate of disintegration or the activity R is equal to minus dN by dt. But here the negative sign indicates that the activity decreases with time. But already we derived the law of radioactivity decay, or the law of radioactive decay. dN by dt is equal to minus lambda n. Therefore, minus dN by dt is equal to lambda n. Therefore, R is equal to lambda n. Right? But we know that the exponential law of decay, radioactive decay, n is equal to n0 e⁻² minus lambda t. Right? Therefore, R is equal to lambda n. R is equal to lambda n. Here we substitute the value of n. Therefore, R is equal to lambda n0 e⁻² minus lambda t. This lambda upon n0 is a constant, that means the initial activity of a substance. Therefore, R is equal to R0 e⁻² minus lambda t, which is the another form of radioactive decay law. And also, we can write the M is equal to m0 e⁻² minus lambda. Clear it? Okay. Again we repeat it. The question is that define the disintegration rate or the radioactivity of a sample and derive the relation R is equal to lambda n. Now, the number of disintegration nuclei per unit time is radioactive in a radioactive sample is known as the decay rate or radioactivity R. Again, the number of disintegration nuclei per unit time in radioactive sample is known as the decay rate or radioactivity, and that is denoted as capital R. Suppose at time t, the number of nucleus in a sample is n. Then the rate of disintegration or the activity R is defined as R is equal to minus dN by dt. Here, negative sign indicates that the activity decreases with time. Activity decreases with time. Okay. Now, from the law of radioactive decay, we know that dN by dt is equal to minus lambda n. Therefore, minus dN by dt is equal to lambda n. We substitute here the value of dN by dt. Therefore, R is equal to lambda n. Therefore, from the equation of exponential law of disintegration, n is equal to n0 e⁻² minus lambda t. Here we substitute the value of n. R is equal to lambda n0 e⁻² minus lambda t. Lambda into n0, that is the initial radioactivity of a sample. Therefore, R0 e⁻² minus lambda t, equation 2. The similar way, we can also write m is equal to m0 e⁻² minus lambda t. So these are the different forms of exponential law. Right? After that, give the different units of radioactivity and define them. And what is the relation between them? Now the SI unit of radioactivity is becquerel, that is denoted by BQ. Named after the discoverer of radioactivity, Henry Becquerel. Again, the SI unit of radioactivity is the becquerel, named after the discoverer of radioactivity. What is the definition of 1 becquerel? The activity of a substance on the sample having 1 disintegration per second is known as the 1 becquerel. Again, the sample having the 1 disintegration per unit time, or in 1 second. The activity of a substance is known as the 1 becquerel. Again, the activity of a substance having 1 disintegration per second take place is known as the 1 becquerel. Therefore, mathematically 1 becquerel is equal to 1 decay take place in 1 second. Therefore, 1 becquerel is equal to 1 decay per second. 1 decay per second. Now, second is the QE unit. The activity of a substance in which 3.7 into 10⁻10 disintegration per second take place. Again, the activity of a sample in which 3.7 into 10⁻10 disintegration per second take place is known as the 1 QE, and that is denoted by CI. Therefore, 1 QE is equal to 3.7 disintegration per second. Disintegration per second. And that is also known as the 1 QE is equal to 3.7 into 10⁻10 becquerel. There is a relation between the QE and becquerel. 1 QE is equal to 3.7 into 10⁻10 becquerel. In practice, it is a smaller units. Its smaller units are of a QE, 1 milliQE, 3.7 into 10⁻7 decay per second, or there is the 10⁻³ minus 3 QE. 1 microQE is equal to 3.7 into 10⁻4 decay per second is equal to 10⁻² minus 6 QE. And other unit is Rutherford's unit. Rutherford unit. The activity of a substance in which 10⁻6 nuclei decay per second is known as the 1 Rutherford. Again, the activity of a substance in which 10⁻6 nuclei decay per second take place. The activity of a substance is known as the 1 Rutherford, or the 1 RD. Therefore, 1 Rutherford is equal to 10⁻6 decay per second. Again, the 1 Rutherford is equal to 10⁻6 decay per second. Now, here the unit of the radioactivity are 3. One is the becquerel, second is the QE, third is the Rutherford. SI unit of the radioactivity is the becquerel. Right? The Henry Becquerel found the radioactivity. Now, the definition of the 1 becquerel is that activity of a substance having 1 disintegration per second is known as the 1 becquerel. Therefore, 1 becquerel is equal to 1 decay per second. Now, the practical unit of the radioactivity is QE. The activity of a substance in which 3.7 into 10 is to 10 disintegration per second take place. That means the 3.7 into 10 is to 10 nuclei disintegrated per second. So the activity of a substance is known as the 1 QE. 1 QE is equal to 3.7 into 10 is to 10 disintegration per second or the decay per second. Now the smaller units of QE are 1 milli QE, 3.7 into 10 is to 7 decay per second, that is also 10 is to minus 3 QE. 1 micro QE, 3.7 into 10 is to 4 decay per second or 10 is to minus 6 QE. Another unit of radioactivity is Rutherford. Rutherford unit. The activity of a substance in which 10 is to 6 decay per second take place. Again, the activity of a substance in which 10 is to 6 nuclei decay per second is known as the 1 Rutherford. Therefore, 1 Rutherford is equal to 10 is to 6 decay per second. So keep in mind these units because for MCQ type question frequently asked. Okay, now after that the discussion of the decay constant and also the exponential law of radioactive decay. Now what is the half-life, and now obtain the relation of the half-life with the decay constant or the radioactive constant. Right? The question is that what is the half-life of a radioactive substance and obtain its relation with decay constant. Or sometimes this question is also asked like that way. Define the half-life and obtain tau half is equal to 0.693 upon lambda. This question is most important because frequently there is asked for the 2 marks question. Earlier question is the exponential law of radioactive decay is also most important, and second is this. What is the half-life of a radioactive substance and obtain its relation with the decay constant. Or define half-life and obtain the tau half is equal to 0.693 upon lambda. Already we discussed about the decay curve, that means the graph of number of undecayed nuclei versus the time t. And in the characteristic of this curve, we can also calculate the rate of disintegration and also the half-life of a radioactive sample from the graph. Right? Half-life is the time interval for which the number of nuclei of radioactive element reduced to half of its initial value. Again, the time interval during which the number of nuclei of radioactive element reduced to half of its initial value. Such time interval is known as the half-life. Is known as the half-life of a radioactive substance. It is denoted by tau half. It is denoted by tau suffix half. Okay. So there is the definition of a half-life. Again we repeat it. The time interval during which the number of nuclei of a radioactive element reduced to half of its initial value. Right? Is known as the half-life. Okay. It is denoted by tau half. Now, the equation of the exponential law of radioactive decay, n is equal to n0 e⁻² minus lambda t. Why we consider this equation? Because this equation is related with the final, that means the number of undecayed nuclei at time t, n0, number of undecayed nuclei at initial, that means the time t is equal to 0, and relation with the decay constant and also the time. This equation relates with number of nuclei, decay constant and time t. Suppose at time t, if we consider t is equal to tau half time, at that time the number of undecayed nuclei becomes n0 by n. That means in tau half time interval, the N0 by 2 nuclei are, that means the half nuclei are decayed. Therefore, the remaining nuclei is N0 by 2. We substitute this value of tau of t is equal to tau half and n is equal to N0 by 2 in this equation. Therefore, N0 by 2 is equal to N0 as it is, E is 2 minus lambda into tau half. N0 and 0 cancel, therefore half into E is 2 minus tau half. Now, 1 by 2 is equal to 2 is 2 minus 1. 2 is 2 minus 1. But 1 by 2 is equal to E is 2 minus lambda tau half. So it's equal to E is 2 minus lambda tau half. Right? Taking the positive power of both, because both are in denominator. Right? Therefore, we can add 2 is equal to E is to lambda tau half. E is to lambda tau half. Taking the ln on both sides. Why ln not log? Now listen, the difference between the ln and log is, ln is base e, while the log is base 10. Log is base 10. Here in form of exponential, therefore we are considering the ln not log log. Therefore taking the ln on both sides, therefore ln2 is equal to E is to tau half into ln E base E. E is to tau half ln base E base E. ln E base E is equal to 1. Now one more the property of this ln. X is to A. So that can be written as the A ln X. Yeah, we are using this concept, the power of E is in multiplication lambda tau half into ln E. ln E base E is equal to 1. Therefore, ln2 is equal to lambda tau half. Now we have the log table on the base of the 10, not on the base of E. Therefore, we have to convert the ln into log. The relation between the ln and log is this. ln is equal to 2.303 log log. ln is equal to 2.303 log log. Therefore, instead of the ln2, we can add the 2.303 log 2. Therefore, 2.303 log 2 is equal to lambda tau half. We require the equation of the tau half. For that purpose, we need to substitute the value of log 2. In log table, log 2 is equal to 0.3010. Therefore, 2.303 into 0.3010 is equal to lambda tau half. Now the multiplication is 0.693 is equal to lambda tau half. Therefore, tau half is equal to 0.693 upon lambda. That is the relation between tau half and decay constant or the radioactive constant. So this equation frequently we are using in numerical. If the lambda is given, we have to calculate the tau half. So tau half is equal to 0.693 upon lambda. Or the tau half for a radioactive substance is given, calculate the decay constant or the radioactive decay. So we can obtain the lambda is equal to 0.693 upon tau half. Clear? So from this equation, the half-life of a radioactive substance is inversely proportional to the decay constant. Is inversely proportional to the decay constant. Again, we repeat this answer of the question. Now, what is the half-life of a radioactive substance and obtain its relation with the decay constant? Or in other words, define the half-life and obtain tau half is equal to 0.693 upon lambda. So first the definition of the half-life. The time interval during which the number of nuclei of radioactive element reduced to half of its initial value. Again, the time interval during which the number of nuclei of radioactive element reduced to half of its initial value. Such time interval is known as the half-life, and it is denoted by tau half. Right? Now, exponential law of radioactive decay. So, N is equal to N0 e⁻² minus lambda T. If the T we consider as a tau half-life, at that time the N, number of undecayed nuclei, becomes the N0/2. Because in time tau half, the half number of nuclei are disintegrated. Therefore, N is number of undecayed nuclei is N0/2. Substitute T as tau half and N is equal to N0/2 in this equation. Therefore, N0/2 is equal to N0 e⁻² minus lambda tau half. N0 cancel. Therefore, 1/2 is equal to e⁻² minus lambda tau half. So here the power is negative. We can add the 1/e⁻² lambda tau half. Comparing the denominator of this term. Therefore, 2 is equal to e⁻² lambda tau half. Right? Now we are interested to obtain the equation of the tau half. For that purpose, we are taking the ln on both sides. Now first, what is the difference between the ln and log? Why we take the ln? Because here the exponential form base is e. Therefore, ln is base e, while the log is on the base of t. Taking the ln on both sides, therefore ln2 is equal to, here using this concept, ln x raised to a, therefore a ln x, therefore lambda tau half into ln e. Ln e is 1, its value is 1. Therefore, ln2 is equal to lambda tau half. ln2 is equal to lambda tau half. Keep in mind this relation. What is the relation between the ln and log? ln is equal to 2.303 log. ln is equal to 2.303 log. Substitute here. Therefore, 2.303 log 2 is equal to lambda tau half. Now we substitute the value of log 2 from the log table. Log 2 is equal to 0.3010. Therefore, 2.303 into 0.3010 is equal to lambda tau half. Therefore, multiplication of these two terms is 0.693 is equal to lambda tau half, and therefore tau half is equal to 0.693 upon lambda. That is the relation between the half-life and decay constant. Clear? So from this equation, one can say that the half-life of a radioactive substance is inversely proportional to the decay constant or radioactive constant. Now we can also define the half-life from the disintegration rate. Now we define the half-life from the disintegration rate. Disintegration rate, that means the activity of the substance. Now, the definition of the half-life from the activity. Activity is dN by dt. dN by dt. Right? So, the time period in which the activity of a radioactive substance becomes the half of its initial activity. Such time interval is known as the half-life of a radioactive substance. Again, the time period in which the activity of a radioactive substance becomes the half of its initial activity. Such time interval is known as the half-life. Clear? Okay. Now, remember that we drew the diagram of the decay curve. Initially, the number of undecayed nuclei is N0. As the time increases, the number of undisintegrated nuclei is also going to decrease. Initially, the number of undecayed nuclei is N0. So, there is a half N0/2. the time for which there is the tau half. For this time, the number of undecayed nuclei becomes the half of initial. So this time interval is our half-life. That is denoted by tau half. Already we discussed in decay curve. Again, in the same time interval, its number of undisintegrated nuclei becomes again the half of this n0 by 2. Therefore, n0 by 4. Another next tau half time. Third half life again becomes the half of the n0 by 4. Therefore, n0 by 8. Right? And also, according to the characteristic of decay curve, the activity or this rate of the disintegration of the nuclei per second. Initially, there is the quickly. As the time passes, the number of undisintegrated nuclei decreases. Therefore, the rate of disintegration also becomes the slower. So, whatever the activity at time t is equal to 0, at time tau is equal to half, the activity becomes the half of the initial. So, this time interval is also known as the half-life. To explain this thing, I do this decay curve. The time period in which the activity of radioactive substance becomes the half of the initial activity R0. Right? So this time interval is known as the half-life of a substance. That is known as half-life. Clear it? Okay. So that is the most important question. What is the half-life, and obtain the relation of a half-life with the decay coefficient. Clear it?